Arjun, working as assistant professor in Department of Mechanical Engineering, Sai with the Institute of Technology. So, in today's session, we are going to discuss some important topic in tribology, which is Reynolds equation in 2 dimensions. This is so in order to explain this Reynolds equation in 2 dimension, I have considered a converging oil film. Considered a converging oil film, and in that, we have taken a small element for analysis. That element is expanded, and the forces acting on this fluid element with respect to x direction are shown here. This is a normal stress acting, and this is a shear stress acting with the increment along with the incremental stresses. So while deriving Reynolds equation, we do make certain assumptions. So the first assumption is there is no flow in the direction perpendicular to motion. So this is assumption number 1. And assumption number 2 is the viscosity of the lubricant is considered constant throughout the oil film. So in this particular oil film, the viscosity of the lubricant is considered as constant, and the motion of the fluid film is laminar. And the fluid flow in this converging oil film is laminar. And the inertia forces in the oil film are usually so small, such that the influence on the pressure developed in the film will be neglected. Influence on the pressure developed in the film may be neglected. That is assumption number 4. And assumption number 5 is there is no slip occurs between the lubricant and the bearing surfaces. Slip is neglected. And assumption number 6 is the fluid is incompressible. And assumption number 7 is the shear stress is directly proportional to the rate of shear. This makes the fluid as Newtonian fluid. And assumption 8 is the clearance between two bearing systems is so small, so that the changes in pressure across the surfaces can be neglected. These are the few assumptions where we make in deriving Reynolds equation. These are the few assumptions that we make in deriving Reynolds equation. To continue with that, so let us take the forces acting in x direction and equate it to 0. Let us consider the forces which are acting in x direction and equating that forces to 0. So we can consider P is a force which is acting in particular x direction. P is a force which is acting in particular x direction. So P into, since it is acting in x direction, we can take y and z component, P into dy dz minus of P, so into dP by dx. So it is acting in x direction into dx. So since it is x direction, so we can consider y plane and z plane, dy and dz, plus we have shear stress tau x into dx dz, since it is acting in y plane, and minus of tau x plus d tau x divided by dy into dy into dx into dz, so which is equals to 0. These this particular values, these equations are considered from this particular equation. So this is taken as positive, this is taken as negative, this is taken as positive, and these forces are taken as negative. So summing all the forces which are acting in x direction, since we told that there is no flow in the direction perpendicular to motion, we assume there is no flow in this direction perpendicular to motion, and we have considered the fluid forces on the fluid acting in the x direction, and we have equated the forces which are acting in x direction to 0. So this is how the equation looks. And if we cancel these terms, this term and this term, this positive and this negative, so finally we will be left out with minus dP by dx. So, and if you multiply these values, dx, dy and dz, so plus minus, so here we will be left out with d tau x divided by dx into dx, dy and dz equated to 0. And if you take the other term, so minus dP by dx into dx, dy, dz, and let us transfer this to the right hand side. So minus will become plus d into tau x divided by dx into dx dy dz. So if you can cancel the small elemental dimensions dx dy dz. So finally, so minus dp by dx can be treated as equals to d into tau x divided by dx. So you can call this as equation number 1, for instance. So from Newton's law of viscous forces, okay, Newton law of viscous forces, we know that the rate of shear is directly proportional, shear stress is directly proportional to the rate of shear. So you can rewrite this tau x as, so absolute viscosity eta into dou u by dou y, where dou u is a velocity at each element of the converging oil film, each layer of the converging oil film, dy is the thickness of each layer of the converging oil film. Since there will be some coefficient of friction, so we can take this as negative minus eta into dou u by dou y. So let us substitute this value into this equation. So now equation 1 will imply minus dp by dx, okay, minus dp by dx is equals to minus of d divided by, okay, minus e directly dy of, so now in the place of tau x you can write du by dy, so du by dy. So on simplifying you can write this particular function as, so you can cancel this minus and this minus, so dp by dx will be equals to eta into d square u by dy square, d square u by dy square, or in other words d square u 1 over eta. So if you transfer the eta to the other side, so dp by dx. Now let us integrate this equation with respect to y. So now this will become du by dy is equals to 1 over eta into dp by dx into, since we are integrating this with respect to y, into y plus c1 is a constant of integration. Now again integrating this equation, so you can write u is equals to 1 over eta dp by dx. So integral of y is y square by 2 plus c1 into y plus c2. Okay, now you can call this particular equation as equation 2. So we can call this as equation 2. So in order to find out this constants of integration c1 and c2, let us apply boundary conditions. So applying boundaries, okay, applying boundary conditions, that is 1 at y is equals to 0, okay, at y is equals to 0, so value of u will be u. So this is when the fluid is in motion, and at y is equals to h, so at y is equals to h, so u will become equals to 0, that is at the contact surfaces, so where the fluid motion will be constant. That means to say you can consider these two conditions. So this is when y becomes equals to 0, and this is when y becomes equals to h. So here the velocity will be u, and here, so velocity at the contact surfaces, because it is a stationary member, here it will be 0. So that is what the initial boundary conditions that we are going to apply. At y is equals to 0, so u will become capital U. So now this equation 2 will imply, so u is equals to 1 over eta, so this entire term will become 0. So dp by dx into 0 by 2 plus c1 into 0 plus c2. So we'll get c2 as u. We'll get to know the value of c2 as u. Okay, now since we found the value of c2, since we found the value of c2, okay, let us continue to find out the value of c1. So now we shall apply the second boundary condition, that is at y is equals to h, value of u will become equal to 0. Again our equation 2 will imply 0 is equals to 1 over eta dp by dx. So y square by 2 instead of y, it will become h square by 2 plus c1 into y, so it will become c1 into h plus c2. Since we need to find out c1, so I'll take c1 into h and I'll transfer the remaining to the other side. So 1 minus of 1 over eta dp by dx to h square by 2 minus c2. So we know that value of c2 is u. So and similarly let us transfer this u to the other side. So now c1 will become, so 1 over h into 1 over eta into dp by dx h square 2 by h. Again we will be transferring this h to the other side, so you can cancel 1h. So c1 will become, so minus h divided by 2 eta, so we have 2 into eta dp by dx minus u divided by h. So now let us substitute the value of u1 and u2 into equation 2. So now that u equation will become 1 over eta into dp by dx into y square by 2 plus c1 into y. C1 is minus h divided by 2 eta into dp by dx minus u by h into y, so plus c2 is u. So let us write u as it is. So u is equals to, so 1 over 2 eta, so you can directly write 1 over 2 eta dp by dx into y square, so minus h into y. So let us separate these two values, h into y divided by 2 eta into dp by dx minus, so u into y divided by h plus u. So now in these two terms you can take 1 over 2 eta into dp by dx as common, so u will become 1 over 2 eta into dp by dx. If I take dp by dx as common factor in these two, 1 over 2 into dp by dx, so we have y square here minus, so we have h into y this term, and plus if you take out u as common in this, we have h. Okay, if you take LCM, so we'll have h minus y divided by h. Okay, this is a equation for flow flow. This is a velocity distribution. Okay, this is the equation for velocity distribution of a converging oil film, So to continue further, so let us consider velocity distribution of a oil film, where you can take these values. So if you write this diagram, okay, so now let us consider a three-dimensional flow here. So u into, so this is u, this will be v, and say x, y and z direction. So let us consider, since we are talking only of 2 dimensions, so let us take u, the flow in x direction. So x plane will have y and z direction, so y plane will have z and x direction, dx into dz. So z plane will have x and y directions. Since we are deriving the equation only for 2 dimensions, we can treat this as 0, and So in order to rewrite this, so which will be equal to again, sorry, this will be equal to the incremental directions. So dou x into dx. So since it is explained, we'll have y and z component. So similarly, v plus dou v by dou y into dy. So since it is y plane, we'll have x and z component, and w, so with respect to incremental directions, dou z into dz, so into dx dy. Again we can treat this as 0. So now if we cancel these two terms, finally we will be left out with u into dy dz is equals to, sorry, plus v into dx dz is equals to, so if you simplify this, u into dy dz plus dou u by dou x into dx dy dz plus v into dx dz plus dou v by dou y into dy into dx dz. So we can cancel this positive term and this term, this term and this term. So finally we'll be left out with these two variables, that is, so finally, so if you transfer one to the other side, so we can write du by dx into dx dy dz, and if you keep this on the left hand side and you transfer it to right hand side, so dv by dy dx dy dz. So we can cancel the small elemental dimensions, that is dx dy dz, dx dy dz. So you can rewrite this function as, so you can rewrite this function as, so finally we know that dv by dy is equals to minus of du by dx, okay, where you can write this elemental volume dv is equals to minus of d by dx of u, this u into dy, where this u is a velocity distribution of a converging oil film, and since this velocity will be 0 when y is equals to 0 at contact surfaces, at both the contact surfaces, and y is equals to h, so you can consider between the limit 0 to h, and this velocity will be is equals to 0. Velocity of a small element in that particular direction can be treated as equals to 0. So now since dv is equals to this value 0 to h, so minus of d into d by dx of u into dy can be treated equals to 0. So minus of d by dx, so let us consider like this. So we'll take the velocity of the converging oil film into dy is equals to 0. Since we know that u is equals to 1 over 2 mu dp by dx y square minus h, so let us substitute that equation here. D by dx of integral of 0 to h, so 1 divided by 2 mu into dp by dx, so y square minus h into y plus u into h minus y divided by h, okay, into dy. So let us take one term at a time. So minus, so let us take one term at a time, minus d by dx of 0 to h 1 over 2 eta dp by dx y square into dy. So one term, the second term, so minus into minus will become plus, so 1 over 2 d by dx of 0 to h 1 over 2 eta dp by dx into, so we have h into y into dy, and finally we take this term, so plus into minus, so it will be minus d by dx of integral of 0 to h, so h and h will get cancelled, so u into, so dy plus, so now minus into minus, it will become plus d by dx of integral 0 to h. So so let us simplify this particular function. So on simplification, so now we'll take this function minus d by dx. Okay, if you take the first function over here, 1 over 2 eta dp by dx. So integral of y square is y cube by 3 between the limits 0 to h. So plus d by dx. So we can observe this 1 over 2 eta dp by dx. H into y, integral of y is y square by 2 between the limits 0 to h, minus d by dx cube into y plus d by dx u into h y square by 2 0 to h and equal to 0. So now minus d by dx. So when you apply the upper limit, so it will become h cube 1 over 2 eta dp by dx h cube by 3 plus d by dx 1 over 2 eta dp by dx. Now h square into h, it will become h cube by 2 minus d by dx. So u into h plus d by dx. So we have u into h square. So 1h and 1h will get cancelled. So that is u into h square by 2 equals to 0. You can cancel 1h and 1h. And now in these two terms, if you take 1 over 2 into d eta by dx, or you can rewrite like this, d by dx of 1 over 2 eta dp by dx. And if you take h cube as common, so we can directly write. So we have here 1 by 2 minus 1 by 3 in this case, plus d by dx of u into h. If you take u to h as common, so we have 1 over 2 minus 1. So here in this case 1 over 2, we have minus 1 here, equated to 0. And on simplification, d by dx of over 2 eta dp by dx h cube. So if you take LCM, so this will become LCM and simplify, so it will become 1 by 6 plus u into h to minus 1 over 2. So we can equate this to 0. So this will become now d by dx of, so 6 2s are 12, 1 over 12 into eta h cube into dp by dx plus minus d by dx of u into h by 2 equals to 0, or you can transfer the d by dx of 1 over 12 into eta h cube dp by dx is equals to d into h. So if you take this term here, d into h into u divided by 2, so 2 1s are 2 6s are. So on simplification, d by dx of dp by dx into h cube will become 6 u into eta. So I'll transfer this to the other side, dh by dx. This is a Reynolds equation in 2 dimension. This is a Reynolds equation in 2 dimension. Thank you.